Hello, my name is Victoria Grimes, and this is Lab 2, where we revisit the Lab 1 with charge tapes. The purpose of this lab was to utilize household objects such as tape to demonstrate and observe the transfer of electrons between surfaces and determine the respective charge of the tape. Some of the fundamental principles that we used in this lab was Coulomb's law, which we used tape to model point charges, and we assumed equal and distributed charges across the tape to use this principle. We used Newton's second law, where F equals ma, and Coulomb's law to calculate charge on each tape piece, and we also used approximate dimensions of an atom to calculate the number of deficient or excess electrons per atom on a charged tape piece, and we also used the principle of superposition. So for a quick preview, the charged pieces of tape were determined to be positively charged because they repelled each other, and the charge on each tape piece with the line charge model was 2.316 times 10 to the negative 8 coulombs. Unlike Lab 1, we did not model the tapes as point charges. Instead, each tape piece was modeled with a distributed charge along the length of the tape, and our assumptions were that there was no air resistance. We treated the long tape as though it were a point charge with all the charge concentrated at the center of the long tape, and each U-tape piece had an equal surface distribution of charge. So for our experimental setup, we have our system and surroundings. System is tape A and tape B, and the surroundings were everything else in my room and outside. The initial conditions were 2 pieces of tape assumed to be neutral and equal in length, and also 2 pieces of neutral tape stuck down onto the desk. And the process was that tape A was stuck to the tape on the desk to create a charge. Tape A was hung around several objects to determine its charge, and then tape B was charged similarly. Tape A was placed above tape B until a portion of tape A floated, and the distance between the 2 tapes was measured to later calculate the charge. Pictured on the right is the setup that I had. It's kind of jank. And pictured on the left is a demonstration of the tape floating. Now on to our observations. So we figured out that the U-tape, tape A, was attracted to my hand. Tape A was also attracted to a neutral pack of cards as seen on my desk. Tape A was also attracted to a negatively charged plastic cap on a pen, and tape A was repelled by tape B, as you could see in the previous slide. And the conclusion was that tape A and tape B were positively charged and lost electrons in the charging process. For our data and calculations, so we have the tape mass, tape length, tape width, and the distance between the tapes. And then we apply Newton's second law, which is F equals ma, which is also equal to mg, and g in this case is 9.81. But we know that the acceleration for the tape is going to be equal to 0, so our forces are balanced. So our electric force and gravitational force are balanced, and with this information, we were able to calculate what the charge on a piece of tape was. Furthermore, we were able to calculate the number of electrons lost by a piece of tape by dividing the charge of the tape we just found by the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs, and we got 6.56 times 10 to the 10 electrons. We also found the area of a tape, the area of an atom, and so the number of atoms on the tape were going to be the area of the tape divided by the area of an atom, and we got the ratio of electrons to atoms by just dividing the 2. This was the glow script code. We inputted data from Lab 1 into the code, as well as the charge that we found in the first experiment, which was 1.05018 times 10 to the negative 8 coulombs, and we use this to calculate what the line charge model of this object would be. So here on the right, we have what this system would have looked like. And the model discrepancies are that we don't have any real point charge, and the charges on each tape likely have unequal charges, and some sources of experimental error are that there are unequal charges on each tape, meant that Q is likely not the same for each, and you have a charge transfer when handling the tape, and also humidity. Finally, to the conclusion, what if the tapes were modeled as a single point charge? So the point charge model gave us a charge of 1.0501 times 10 to the negative 8 coulombs, and the line charge model gave us 2.316 times 10 to the negative 8 coulombs. And after taking this ratio, you got a 45% difference. And so why do the estimates differ, and what is closer to the real value? So the reason why the estimates differ is because there are different levels of precision used. The line charge model is likely closer to the real value since it uses smaller step sizes and provides a better approximation. And so from this, we get that everyday objects can be used to observe electric forces at a play on nanoscale. Common objects can be easily charged to touch alone, and electric forces and fields are important information and play a large role in how we interact with the world around us.